In this method, we're going to talk about finding a volume using the disk method, but we will be rotating about the y-axis. And so the only thing that is different here is that when we talk about our radius, instead of having y as a function of x, we're going to have x equals some function of y. And you'll notice that the bounds change from C to D. We just use that nomenclature when we are dealing with a rotation with respect to y, or integrating with respect to y, I should say. So let's put the problem up. For this problem, we're going to find the volume of the solid generated by revolving the region between the y-axis and this curve about the y-axis. So the function we're given is y equals 2 over x, and we're going to be considering this function over the vertical interval where y is between positive 1 and 4 inclusive. So whenever we're finding or working these volume problems, it's always helpful to develop a picture. Think about what that graph or the region is that we're looking at. So I've brought in a nice picture. And one thing we want to notice, now remember, this was given as y equals 2 over x, but I want you to look at how it's written. All right, it's written as x equals 2 over y. Just with some basic algebra, we can multiply y times x equals 2, x equals 2 over y. We can rearrange that equation and isolate the variable. So it's very important when we think about rotating about the y-axis that we have that function x in terms of y as opposed to y in terms of x. And so you'll notice that here. That's the function we're going to use. And considering that with our definition, remember that definition also needs to be this function of y. All right. Also, remember our bounds. Our bounds here are between 1 and 4. So 1 and 4 are my vertical bounds, least to greatest. And what we're doing in this problem is we're looking at rotating this about the y-axis. What would that look like? So if we look at taking that line and spinning it around the y-axis to determine what this three-dimensional region looks like, we kind of end up with this game piece shaped cone. All right, and so you'll notice that the discs are all parallel to the x-axis, perpendicular to the y-axis. And so up at the top we would have a very small disc, and down at the bottom we would have a very large disc. And we have all these discs of varying radii, which is why we use that function to represent the radius as opposed to just a number or a value, because the radius varies. All right, so let's set this up now that we kind of understand what we're looking at to find the volume. So in order to do this, volume, remember, it's going to be the integral from c to d of pi times whatever that radius as a function of y is squared, integrated with respect to y. So in this situation, we're going to have v equals 1 to 4 of pi. My function is 2 over y, quantity squared, dy. All right, so in order to integrate this, I'm going to pull my pi out in front. 2 squared is going to give me 4, and that's going to be y to the negative 2 dy, y squared, and then you move it up to the numerator. So now we have something that is very easy to integrate. I'll go ahead and pull that 4 out in front with the pi. And if I look at just integrating y to the negative 2 using the power rule, I add 1, I get negative 1 over negative 1. So I've got y to the negative 1 over negative 1 from 4 to 1. So I've got negative 4 pi y to the negative 1 from 4 to 1. We'll plug in 4 and we'll plug in 1. Plugging in 4 gives me 1 over 4, and plugging in 1 gives me 1 over 1. So I have 1/4 minus 1, which of course is going to give me negative 3/4. So negative 4 pi times negative 3/4 is going to be positive 3 pi. And that represents the volume of that curve rotated about the y-axis. So I'll do a few more videos in this series, but I hope that kind of helps you with the disk method. And I want you to notice as we move forward, this disk method really builds towards being part of the washer method, right? So we have a washer method that we'll talk about, and we'll also have a shell method. All right, and those are going to be our more advanced ways for integrating and finding volumes. One thing, I'll skip back to the beginning. One thing I want you to notice is that this curve was right up against, we're looking right up against the y-axis. But we could be dealing with a problem where maybe we're integrating and we don't have that space included, right? So there could be like a hole down the center of this volume here that's cut out. And so we'll look at regions where they are shifted away, or maybe we have 2 different radii. As always, email me if you have any questions.